Welcome to today's Summer Provost Lecture Series by Dr. Giovanna Oriti, What Will Keep the Lights On, Microgrids, Energy Security, and Climate Change. Professor Oriti received her doctorate in electrical engineering from the University of Catania, Italy. She worked at United Technologies Research Center, where she developed innovative power converter topologies and controls and has run her own consulting business. In 2008, she joined the faculty of the NPS Electrical and Computer Engineering Department. She is highly published and has received numerous awards, including the IAS Outstanding Young Member Award and NPS's own Richard Hamming Faculty Award for Interdisciplinary Achievement Excellence. She is very active across the board, but especially with the IEEE, serving in numerous leadership positions and leading as an IEEE. That's just killing, you know. I gotta say, IEEE. I know, but not everybody else knows that. I'll just say IEEE senior member. Giovanna is going to speak, and then we'll take online and in-person questions. We'll stop at 1600 sharp, followed by refreshments and continued informal discussions. And there's refreshments outside. In particular, if you're thirsty, go grab a water bottle. I'll help you to do that. So all good? And with that, please join me in welcoming Dr. Giovanna Oriti. Giovanna?
Thank you, Provost Gardner, and thank you everybody for being here and giving me an opportunity to talk about a topic that I'm really excited about, which is microgrids and lights. So let's get started and start with the opposite of light, which is darkness, right? When the lights are out and everybody is pretty unhappy because it seems like all our lives are run by devices that require electricity. They need to be plugged in into the wall. We need electricity in one way or another, and seems like we can't really do much without that. So the classical way is that we just wait. We do what we can with candles or whatever, you know, batteries on our cell phones, and then we wait for the power company to fix the problem, right? We recently had this experience here on the peninsula, unfortunately, and we all know how we have difficulty adapting to a darkness situation where we don't have electricity. But eventually the light comes back and we're all happy. So let's talk about what happens when the lights are out, and this concept that is critical loads. Critical loads I want to introduce in daily life, right? Those are loads. Electrical loads are basically things that need to be plugged into the wall that require electricity to work, right? So those are what we call loads. Critical means that you can't live without them, or at least that it's really bad if you don't have them connected to the wall, right, to the electricity. And one thing, for example, that we can all relate is the refrigerator, right? There is food in the refrigerator that will spoil if we don't have electricity for an extended amount of time. So, and there is a cost also associated with the loss of electricity, right? I have about, $200 worth of food that is gonna go to waste if I don't have electricity back on time. But there are other things that are what I would call non-critical loads, like the coffee machine. And here is where we disagree with my students. When I talk to my students about non-critical loads and I say the coffee machine is non-critical, they scream. No, it's not. It is a critical load. So anyway, regardless of how you see the coffee, there is also a cost associated with lost productivity, right? You can't function without coffee, or you can't function without certain machines that you need in your job in order to be productive, to do your job. So in either way, you can associate a dollar amount on the lack of electricity, on the fact that you lost electricity, there is no power. But what about for the Department of Defense, right? The Department of Defense is different. Yes, there will be refrigerator with food that spoil. Yes, there will be coffee machines that are badly missed, but there is something else. There is a mission, right? Each operation, each base, in this case, I'm showing a forward operating base, and an installation, the one in which we are right now, they have different missions. Each mission requires different critical loads, right? So there is a different cost, a different penalty associated with loss of electricity, depending on what mission is that operation pursuing, right? So it's not so easy to translate into dollars or to put really a finger on what it is that is wrong when there is electricity lost for these cases. So let's talk about how power is available on bases besides the power coming from the utility company. So there is the traditional generators. And these pictures show example of a genset on a forward operating base. This is a typical genset that you will see on a forward operating base, but there are also backup generators on facilities like the facility we have here on campus, right? There are backup generators on campus, and traditionally they're connected to either a single load or very few loads. This is what we learned with my students from the US Marine Corps briefs in the past. But there is another thing about these generators. First of all, they produce CO2, they're diesel, they burn fuel. Second of all, they're typically oversized. So for example, and this again is from a brief from the US Marine Corps, where a genset of 65 megawatt service load of 32 megawatt, right? It's half about the size. So why are they oversized? Because just in case there is a growth, a need for more power, then we make them bigger than they need to be. But this comes with a penalty. The efficiency of this generator is much lower when the load is lighter. So the lighter the load, the farther away from the rating of the generator, the more fuel you burn. So it's not efficient. Second thing is they often carry with them load banks, which means they're fake loads, means things that dissipate energy on purpose. Because so that way you add more load to the generator, and the way there is no chance of going into this situation called wet stacking here. And wet stacking is a term that is not easily known. So I copied it from Wikipedia, and it's mostly for mechanical engineers to know. It's basically when the generator is so lightly loaded that there is unburned fuel into the exhaust system. And basically this reduces the lifetime of the generator. So the generator will last less if you operate a light load all the time. So that's why they use fictitious loads just to burn energy to increase the load. So this basically means there is fuel consumed, there is cost to produce electricity, and there is also cost associated with transporting the fuel to produce electricity, when of course there is a need for backup. So in remote operation, there is sometimes difficult paths to transport the fuel, right? Depending on where these remote operations are located. And in facility, there is the issues with gensets that are usually from different vendors. They require different type of maintenance cycles. Sometimes they're really a nightmare to maintain. Sometimes they're not maintained well and they don't function when they're supposed to function. So there is all kinds of problems with generators. But you can not easily as put a cost as a dollar amount to what it costs to produce electricity with generators. And there is, of course, the ultimate cost, which is casualty due to transportation of fuel sometimes. This is data from 2010 provided by US Marine Corps, where there is, associated casualties with transportation of fuel because, things that can happen during the transportation. So this is to make the point that it's not easy to put a dollar amount like we did for the refrigerator for the Department of Defense when there is loss of electricity, right? There are other things to consider: the mission and the difficulty of transporting fuel that increase cost and produce other problems. Recent goals for the DoD, in two simple bullets: increase energy resilience and reduce fuel consumption to fight climate change. So decarbonization is a word, try not to produce CO2. And this document here talks about the climate action. Well, this document is a DoD-wide document where we can read a quote. I don't expect to read the tiny prints here, but this is a quote extracted by one of my students from this document. Energy resilient solutions are not limited to traditional standby or emergency generators. Those ones I was showing in the previous pictures, right? They can and should include integrated, distributed, or renewable energy sources. So in come solar panels, right? In this picture, you can see the Marine Corps in new expeditionary camps bringing solar panel, renewable energy. Let's talk about definition first. So what is renewable energy, right? And these are some examples. There is more, of course. There is other forms of renewable energy. These are just the most popular that we know. Is energy from sources that are naturally replenishing, like sun, wind, right, or marine power, and they're virtually inexhaustible. So there is unlimited availability, but the amount of energy at any given time is limited. You cannot control when the sun is there or not. You cannot control when there is wind. So it's unpredictable. Well, it could be predictable, but it's not so easy to control. And I added here a chart from the International Energy Administration where we can see over time, and here it's pretty small on the axis, but 2023 is about here, where we see that wind and solar are really going up as far as usage worldwide, where the coal and the natural gas go down. So we're expecting the number of renewable energy sources to be used more and more, and while the quantity of coal burned or natural gas goes down. So this is for renewable energy. So what happens when you have renewable energy is a new paradigm for the grid, right? We have in this picture on the left, there is the traditional grid where there is a large power plants, including renewable too, but typically traditional power plants. They are located in remote location. They produce a large amount of power, and then they send power into the grid, represented by these the tower grids here. And you see how the arrows are black and go only in one direction. See, power only goes from where it's produced remotely into the grid, and then the grid distributed to the consumers, right? There is the system operators that take care of, the power flow. But here is the new paradigm. You see how the black arrows are replaced by red arrows, and the red arrows are bidirectional. So power, energy go in two directions. So because now we have this distributed energy resources defined here from IEEE standard 1547, distributed energy resources are, for example, your solar panel on your rooftop, or your solar panel on the carport, or your micro turbines, or your windmills, etc. They are distributed, means they're no longer centralized in remote location and sending power, but they're distributed everywhere, and they're closer to where they're going to be used than the traditional power plants. So this is a new paradigm with the arrows going in both directions, and is happening more and more because, as we know, in daily life, there is more distributed energy resources. Another thing that we saw in the documents from the DoD I showed earlier is energy resilience. What is energy resilience? And this is one of the key here on my talk. First, I want to show this picture that came out a few years ago in one of the DON documents where energy security was defined, and energy resilience is one of the pillars. But while reliability and efficiency are very well known, and there is lots of analysis tools, design tools available to design for reliability and efficiency, resilience, like my system engineering colleagues prefer to call it, resilience is really not something that a lot of people know about it. There are here some ways to achieve resilience according to the Department of the Navy, but other than that, really it's a vague concept, and I'm going to talk about it some more. First, the definition. Okay, this is the definition that talks about ability to avoid, prepare for, minimize, adapt to, and recover from anticipated and unanticipated energy disruptions. Like the key is the energy disruption, right? What we talked about. The light is out, but we want the light back. And in order to ensure energy availability and reliability sufficient to provide for mission assurance and readiness. These are the key words, right? It's no longer, again, the household where, you know, we lose the refrigerator or the PlayStation and we have our own crisis. Here is the Department of Defense, where mission assurance is the key, and mission readiness. So it's not easy to pinpoint what are the critical loads for the Department of Defense. Only the energy manager on a particular base will know what are critical loads, because they will know what the mission is in the particular facility. So let me explain some more. Besides, you know, keeping the lights on, let me explain some more energy resilience. And here again, thank my colleagues here in system engineering who explained this concept to me for the first time. This curve comes from in a paper that we recently co-authored with one of the students also here at NPS. And so in this picture, we see one key point: disruption occurs, right? Again, this is a non-technical talk, so excuse the picture with the axis, but I'm gonna make it easy. So that's basically when there is the punch, right? Everything is going great and you're doing everything you want. All of a sudden, power is out, right? The lights are out. So what you can do is keep the critical loads on. So you need to somehow show your resilience by keeping at least the critical loads. See, there are some that can be shed, but you have some critical loads that are critical for your mission, and you need to keep them on, right? So that is a measure of how resilient you are. If you are able to keep as much of your critical load on while you are in the middle of a disaster or a disruption, right? And you can see here, this is the time during which the disruption occur, and this is the recovery time. And of course, the faster you recover, the more resilient you are, until, of course, at the end, back in business, the lights are back on and the power is recovered. So you see that the area in that curve gives you an idea of how resilient you can be, right? You take the punch, but you continue to operate and do your mission, carry on your mission until you're able to recover and bring all the lights back on, even the not necessary ones. So this is how energy resilience is explained. So great, energy resilience. The Department of Defense says more renewable energy. Wonderful. We put more renewable energy. We are more resilient, right? Well, not so fast. Let's look at this. Let me tell you a story that started in 2019 as a group of us at NPS here started a project with a naval installation that had just commissioned a few megawatt PV farm, photovoltaic farm, right? With solar panels where, you know, you get sun and you produce energy. They were very happy. They were going to be, saving energy with the solar panel, and they thought they were going to be more energy resilient. But here's what happened. The PV farm shuts down when there is a blackout. So you're back where you started. Yes, renewable energy will save you money, but as far as resilience, is it really helping? Not quite. So lights are still out. So what happens? So what is the problem? Well, renewable energy is not sufficient to increase energy resilience because it doesn't have one thing that big generators in the big power plants have, which is inertia, which is ability to store some energy, right? The energy cannot be stored. So let's clarify this point some more. Okay, let's go into more detail. These power plants, the one that I showed in the previous picture, remotely located, they have generators that are as large as this room or even larger. So these big rotating machines that produce electricity after you burn, coal or whatever it is. That is some kind of energy storage. Renewable energy has no inertia. There is no rotating machine. There is no mechanical parts. It's all electronics. So you get energy from the sun, you transform it into electrons, and you produce electricity, but there is no inertia. If your load requires more or less power, the renewable energy cannot follow. Let me show you some more about this. But first, once you put together renewable energy storage, you need, of course, power electronics, you have a microgrid. And that's what we're going to be talking about in more details next. But let me tell you more about power electronics. What is power electronics? What does it mean? It's my area of expertise, and every time I say, people say, what does it mean? So just in a few pictures, power electronics is everywhere. It's in consumer electronics, is in the electric vehicles. They're power converters. They're devices that convert energy from one form to another. So to charge your battery or to function, whatever it is that is electrical, you'll need a power converter. Your washing machine, your dishwasher, everything, all the appliances require power converters. And a microgrid, for which I have a schematic here, a microgrid requires a power converter, more than one power converter, but a main power converter for sure. Let me show you again in a visual. If you have a load, look at the blue line. The blue line is the energy you consume in your household. So for example, if you turn on the microwave, you have a big spike of power, right? So this is the power you require. If you're connected to the grid or you're connected to a diesel generator, then that generator, the source of power, will follow the load. So they're identical, right? There may be some losses, that's why the difference between the two, but basically one follows the other. So you have a load, the generator will give you whatever the load wants. The load is less or more, and the generator will follow. But not like, it's not the same with renewable energy. With renewable energy, you still have your load. See, the blue line is the same, right? But the power from renewable energy is now the red line. Is not as agreeable as the one from a generator or from the power grid. If there is more wind or more sun, there will be more energy generated, like here. Or if there is less, there will be less energy. If it's nighttime and there is no wind, you're dead. There is no power at all, right? So you need energy storage, right? So what the generators have and you don't have with power converters. So you have, what you do is when you don't have enough power from renewable energy, you take some energy from storage and you use it to augment it to get to the peak. And also when you have too much power, like in the middle of the day, when there is lots of sun, then you store energy and you save it for later. And this from a colleague in electrical engineering class notes. So microgrid. The microgrid allows you to integrate renewable energy with energy storage and take care of the critical loads, shed non-critical loads, connect or not connect to the utility grid, operate with the existing diesel generators, everything in one really nice package. And this is a definition of microgrids. It's not easy to find definition of microgrids. This is from the International Electrotechnical Commission definition. So basically, the key is this power converter that allows to be on or off the grid. Let me give you more detail. These are the two basic states of microgrids: grid connected or islanded. If you're grid connected, this switch is closed, right? You're connected to the grid, you receive power to the grid, but you also collect power from renewable energy, you put it into storage and so forth. And or you can be islanded when the switch is open, which means you are on your own, you don't need the grid, but you produce enough energy from all these sources you have to sustain your load. If you can't, you can shed some non-critical load, but basically you continue business as usual, even when there is a blackout. And the microgrid will do all the work seamlessly. You won't even realize that the microgrid turn on and off, like a generator, right? Like a backup generator. But this one is able to integrate also renewable energy sources. So let me tell you a few more things about power converters. They manage renewable energy sources, and they are the key to follow the grid or form the grid when you are in islanding mode, okay? So, and this without going into details, but the key is to improve resilience, basically, through the microgrid. Let's look at the benefits. So, integrate distributed energy resources, including electric vehicle. More and more electric vehicle can be used as energy storage. You can store energy in the electric vehicle. You can draw energy from the electric vehicle if you want to, if you can, if you have a bidirectional connection. They can service critical load so that they're never interrupted. They harvest energy from intermittent renewable energy sources. So at any time, no matter when there is availability, the energy is collected, is not wasted, and it can be stored if it's not used immediately. And it stores energy when it's and where it's appropriate. And then manages, this is the key, manage the energy, right? So here is where the difference becomes between a commercial microgrid or a residential microgrid and a Department of Defense microgrid. You have algorithms that optimize the functionality of the microgrid, and this can be done with the optimization algorithm, it can be done with artificial intelligence, all kind of algorithm can be used. But the key is figuring out what are you optimizing for? And this is entirely up to the energy manager of the facility. The energy manager only will know what is more critical for the facility. Is it the refrigerators because is this a restaurant, or is this something else because it's a military facility? So the ability to optimize for resilience is something that is not readily available, and that what we have been working here at NPS for. Because first of all, resilience is not very clearly understood, and it's not easy to do analysis or design for resilience. And so it's very difficult to optimize for resilience, where everybody understands optimize for cost, right? Do whatever you can to pay as little as possible to the utility company, right? So store energy, play with the energy, put it in the battery, take out the batteries at the right time so that you pay as little as possible. But for resilience, it's not so obvious. The same for CO2, right? For decarbonization, you want as little as possible. So microgrids are a promising technology to meet the decarbonization and energy goals. But let's see some more about what we're doing here. First, I want to introduce the team. We have been working together for 5 years now, and there is a large group of NPS faculty and students. I only listed a few of the names, but here in this bullet right here, there is about other 50 people, including several students starting from 2019. And faculty from operation research, system engineering, math department, mechanical engineering, energy academic group, electrical engineering. We've been working closely for several years now. And then, of course, we have also the EC laboratory technicians who have been instrumental in any hardware validation we have done. We've also been collaborating with the University of Wisconsin-Milwaukee. And we also been very closely working with NAFAC at the Expeditionary Warfare Center in Port Hueneme here with these people, and then also with naval facilities, both in Italy, in Spain, and also with the US Army garrison in Vicenza, and with ONR Global, which provided funding to people in Europe to continue work with us, and with the National Renewable Energy Laboratory. And this is not all. We already have a collaboration starting with Stanford on decarbonization and several others coming up, because the key is a lot is being done in the technical community in multidisciplines for microgrids. We want to leverage everything. We don't want to reinvent any wheels, but we need to address resilience. That's what we are in a unique position to do here at NPS, which everybody else doesn't do. So that's what we have accomplished so far and what our goals are. We work closely with the people in the field to understand what their needs are, and we already answered some of their questions. I'll tell you quickly a little story. I told you this project started in 2019, and then 2020 was the pandemic, when everybody stopped. Okay, we can't do anything else. We're done. We actually geared up in 2020. We had a unique opportunity because people, energy managers, engineers in naval facility that normally don't have enough time to answer emails from people in academia, they actually were available because they were home, and we got them on Zoom at the right time every other week, and we really picked their brains and learned as much as possible from these people, and we really responded to their needs and started developing tools to design and analyze issues regarding to resilience for these people. So we were really lucky with the pandemic, I have to say, because it gave us this opportunity to acquire knowledge directly from the naval installations and to work with these people very closely. As a consequence, we have developed several tools that we want energy managers in naval facilities to use. And here is our vision, and what we're going to work in the future, we're already working on. So what we learn, one thing we learn is not so much about technology, because the microgrid technology is very well developed. Is sometimes the microgrid technology, it's it cannot be easily deployed, right? There are naval facilities with very large microgrids that cost millions of dollars, and nobody understands how they work, or they struggle to understand how they work, or they have difficult maintaining them and operating them, and they have a huge initial cost. So what we think that it's really the way to go is go in nanogrids, smaller microgrids, smaller increments are in the picture. See this one, this red box, and I have two more identical coming here. Basically, we don't think large investments are required. You can just do one nanogrid on one critical load. Okay, so you have a critical load in your facility and you already have a backup generator. Add a design of a battery and a solar panel or whatever renewable energy you can put in there and create a nanogrid. The nanogrid would be operational on its own as a first box. And then later you get more money, put another nanogrid, another critical load. Then you connect it together. These things do work well together. They are like Legos building block. You can make them work together. They have control system. They can collaborate, cooperate. They are reconfigurable. And we say, let's learn from shipboard power distribution. This is my background. I worked starting 25 years ago. I worked with shipboard power converters for many years as a consultant. And I learned that reconfigurable zonal shipboard power distribution is works very well for resilience. So why not applying to facilities? So here is what this picture basically represents. You lose one zone, you isolate it, you reroute the energy, and you continue to operate, right? So this allows for cybersecurity study. You can incorporate redundancy. It's graceful degradation. You can reduce training for operation and maintenance, and this is a big deal. That's something that we in academia do not appreciate very much. It's replicable, and the preliminary design of such a small nanogrid can be done by anybody, even you for your house. And we developed these wonderful tools, and this website that was set up by one of these, the faculty, Professor Reich, who is right here, basically came from after many iterations of this tool. We developed several tools in MATLAB, Excel, and then eventually Professor Reich came and he did it in Python, and now it's open source and anybody can use it. It's free on the website. So you have a house, you want to design some battery in a PV, go to the website and do it yourself. It's user-friendly. You can do your own account. You can even upload your own load. And this is, of course, once you have your account, you can keep your, the load private, right? Nobody needs to can see it. And then you can basically do a simple design by looking at the simulation in just a few seconds. Now, you will tell me at this point, but what is different? There are lots of other tools that do microgrid design. Yes, there are several tools, including commercial tools that are expensive. What is different with our tools is that we incorporate resilience. Like I mentioned before, resilience wasn't even very well defined for military operation before we started this project. So I think this group here, the NPS, deserves the credit for defining resilience for a military operation with several publications that we have and several theses that we have done over the years. So we have simulation not only of the electrical part, but the resilience part and also some cost. We're also able to do simulations in real time. We're working on digital twins, which I'm not going to get into right now because we want to finish. And then hardware validation recently done by several of the students. And here are some of the names of the students that have been working on these things. In numbers, we have several students, maybe close to 80 or so by the time we add FY 23 and 24. I already mentioned the large number of faculty in campus collaborating and working together and several publications. I want to thank the sponsors too, starting from NAVFAC with the Naval Shore Energy Technology Transition and Integration Program and SETI. The DASN, Operational Energy, ONR, NRP, NASA, we got some funding for lunar microgrids, and ONR Next Step project. In conclusion, microgrids offer a solution to boost energy resilience and to fight climate change. So they are a solution for DoD to meet their goals with the documents that I showed you earlier. And also at NPS right here, right now, we have the right team, and it's pretty much almost all the departments on campus working in one way or another, and several students, and working to give answer to Navy and DoD to reach their goals. The key is continue working in partnership with NAFAC, both in the research, but also as customers to respond to their needs. And also, we want to advance the state of the art, not just for the DoD, but also for the global transition we're doing worldwide to energy transition, right? So we globally want to decarbonization. We globally want to save our planet from CO2 emissions. So we want to integrate more renewable energy, and microgrid is definitely one solution that can help. And we are hoping to help everybody with that, but particularly focusing on the Department of Defense and the Navy and Marine Corps. For anybody interested in more reading, you go to the website where all the microgrid design tools are, and there is also a list of publications, peer-reviewed papers, and also all the theses from our wonderful students here. Thank you, and now we'll take some questions.
Kristen's going to bring a microphone around because we record these and it's easier to hear on the recording. So raise your hand and she'll kind of map out where people are going to go. While we're doing that, Van, do you have an online question that you can? All right, so we'll go first in person. I think there was one over here. Aerobics for the day. Ready for the drum? I think I'd like to know the last cybersecurity. What efforts has been going on here in campus regarding cybersecurity?
Yeah, the mic. Okay. So you're saying you want to know more about the ongoing effort here at NPS?
Regarding cybersecurity.
In cybersecurity. Oh, okay. So cybersecurity in microgrid is very important because these are very intelligent systems that are controlled by electronics. So they're vulnerable to cyber attacks. So we have, as part of our team, we have two faculty, Professor Tula Siraman in electrical engineering and Professor Ale in computer science, and they are looking into methods to make microgrids more cyber secure. Did I answer your question?
Yes, but can you elaborate more on what their work? Or can you elaborate?
What exactly they're working on?
Yeah.
No, I can't. Yeah, I would let them talk about that. That's outside my field of expertise. Yeah, and this is really an effort that just recently started too. It's a very recent effort. It's not something that started 5 years ago with the main team. It's something that we added recently. So yeah, no, we don't have results yet, and I don't know the details because these two colleagues are working on the details, but hopefully soon.
Thank you.
Thank you.
Thanks, Giovanna. So as you're thinking about resiliency, how do you think about resiliency in different areas? So if I'm thinking resiliency at home versus resiliency for an expeditionary force versus resiliency for a manufacturing facility, what is it that helps inform the decisions?
Yes, that's a very good question. That's what I was trying to convey at the beginning of the presentation. It's identifying the critical loads. So I'm talking about electrical energy resilience, right? You have to identify what is the load that is critical to the mission that you're doing, right? If you're a restaurant, your refrigerators, right? Or if you're a home, you have some loads that are more critical than others. If you are in a military facility, the energy manager will know, or the commander for the base will know what loads are critical, what buildings or what particular electronic device is critical for that building. So that determines what you're going to make resilient, right? So for example, once you identify the critical load, you decide that critical load needs to be powered at all times. That light cannot go out. So you want, for example, I think here at NPS, Airman Hall has backup power, right? So when we lost power, Airman Hall was up and going because there was a diesel genset, right? So that is considered critical, obviously. So critical means they when power went out, continue business as usual because there was a diesel generator. we're talking about with microgrids more than just diesel burning fuel, but integrating renewable energy sources. So for example, when power went out, all the solar panels on walk-ins hall, they were completely useless because there is no microgrid. I would imagine the power shut down. The solar panels were not being utilized, even though the sun was out. If you add solar panels in urban hall together with some energy storage, then you could reduce the fuel that you burn to keep the building up. So yeah, resilience for different missions is determined by the different loads, the different electric loads that you need to keep up to support the mission. So if you're on a forward operating base, for example, you will have some critical equipment that you need to keep operational at all time. You may be able to shed some environmental control units for if you're not in the desert. If you're in a moderate climate, you may be able to shed the environmental control units, but you cannot shed maybe your radar and your other critical control devices you need to perform your mission. So being resilient means making sure that those loads are always powered. The lights never go off on those ones, so that you continue to operate. Does it make sense? Thank you.
Thank you for your talk. Looking into the future, is there a concrete way that the Naval Postgraduate School is planning to benefit from the fruits of your research and your group's research?
Can you say it again? I didn't catch it.
So looking into the future for the Naval Postgraduate
Yes.
School, is there a concrete plan to benefit from your group's research as we think about the NPS campus?
As far as the NPS campus, I cannot say. We have been talking to people from public works on campus, and it's difficult. So most of the difficulty we encounter also working with naval facilities or in other places is not so much the technology, but the logistics and the paperwork. So it seems easy. Why don't we just put solar panel, thermal and some batteries and make a microgrid? Not. There is a lot of paperwork seems involved and lots of brick walls to overcome. So it depends on the willpower or the energy manager on the base. That's why you may ask, why in the world are you working with these people in Italy and in Spain? Well, I saw it happen that these guys are very enthusiastic about this technology, and they're willing to go through lots of hurdles to install the microgrids, and they are. And these people really had to sweat to get through the paperwork and the walls for their base commander to accept this new technology in. So at NPS, I don't know. Yeah, we have the energy manager here. We talked to her. She is very open-minded and very interested, but she tells me that there are lots of walls. So hopefully, we do have some microgrids just in the laboratories. Professor Gannon in front of you, he has the oldest microgrid on campus in the turbo propulsion lab at the golf course. And he has had it running for several years, but it's not connected to the grid. It's only islanded and it's only used for research. And we have a couple here on campus too. But other than that, we were hoping that the new building, the Naval Innovation Building, would be a net zero building, right? I mentioned it at one of the meetings that we had, but that didn't go out very well. So I don't know. Yeah, and Gail shaking her head here. Yeah, she's the energy manager here. Yeah.
Maybe you want to explain to the audience the safety problems and the legal problems of backfeeding solar power into the power grid.
Oh, yes.
When there's a failure in the system, you don't want to electrocute a lineman.
Right. Yes, of course, there is the issue. If we go back to the picture, when you have a microgrid, if you have a microgrid that has power loads and you have a fault on the grid, you need to make sure that you open the switch, because when the PG&E sends people to work on the power line, knowing that the lines are down, that there is no electricity, but you are backfeeding power from your solar panels and your energy, it's a problem. So there has to be contracts in places with the utility company to have to be allowed to have a microgrid, you need to have some certain devices, mechanical switches that you can open to make sure that you're really disconnected from the grid when you continue to operate independently. So this is one technical aspect that Professor Fouts was pointing out, obviously. But there are also political aspects and logistical aspects in addition to the technical one. Yeah, thank you.
We got a couple questions online. First one, how do highly nonlinear loads impact the microgrid solution?
How island in the load?
Highly nonlinear.
Oh, an island or linear load. Yeah, it's non-linear loads. It can be easily handled by power converters. So it goes down to a power quality. As a power electronics expert, I'll tell you it's a piece of cake. It's not a problem. Power converters handle nonlinear loads all the time, and they have the ability actually to clean up the power quality too, to overcome the issues that are caused by nonlinear loads. So it's not a problem. In fact, when you're grid connected, you can even be useful to the grid and clean up your current, the current that you receive from the grid, to even compensate for the reactive power that you draw. So you can even actually do without what you usually put at the beginning of a facility, which is capacitors, right, to compensate for reactive power. But now we're getting into electrical engineering words, and not everybody can follow here. But yeah, there is no problem because power converters can handle nonlinear loads. Yeah,
And,
good question.
Next question from online. Are electric vehicles now widely used as power sources or storage for microgrids?
Not, they're not widely used for, it's called V2G, vehicle to grid, when you give power back to the grid from your vehicle. And you, as the owner of an electric vehicle, have the option to actually buy a converter that will allow you to get energy from your vehicle into your house. I don't know about bringing it back to the grid. It is definitely a huge topic for academic research. The number of papers on this topic is huge because it's cool, right? Energy going back and forth, but it's not really very much implemented in real life yet.
So living overseas for quite a few years, I saw how incredibly enthusiastic the Europeans are about just installing wind farms everywhere.
Yes.
And some of the wind farms from farmers that I knew in certain areas had so many wind farms that the farmers were a bit upset. It was all subsidized, so they could install all these everywhere, but they were not designed in such a way that they could actually draw that power all the way back to the power grid. So in the end, a lot of these wind farms, they just had to locally ground because they didn't like do the full design. Is there a way with your microgrid technologies to kind of retrofit these systems where you can have kind of more local battery banks in the area that can, be resilient to the environment in that outside environment where you can actually make use of a lot of those wind farms that are just kind of sitting there looking great, but not doing much?
Yes, and thank you. Definitely, yes. And that's the whole point of a microgrid. You can definitely, if you have a microgrid, then you have power converters that will charge the batteries when you have excess power instead of curtailing it and throwing into the ground. And then you can use the power later, or you can even share with the community, right? Rather than just keeping it for the farm. And you can create a set of nanogrids like we were advocating here for a facility, right? If you have a farm with lots of wind power, then another farm, and each of them is a nanogrid, they can collaborate, share energy, and then of course if one of them has a problem, it goes down, then power can be rerouted and can also be shared with the community. So it's definitely a possibility. The technology is there. It can be done at any time.
The batteries can actually withstand that environment for long periods of time, like if you're setting up kind of a battery type of
the environment, what do you mean? To call
being outside. I mean, everything is
usually they're put in some buildings, they are covered somewhere, because batteries don't perform so well at high temperature or very low temperature either. So it's probably depending on what temperature they have, it's probably best to put them in some kind of shed, I imagine. Yeah, there is another question. Thank you.
Lieutenant Horton. So my question is, I see microgrids, of course, are very important, and I think it's probably going to be the way of the future in how we distribute electricity and power. But I think the way we're communicating it probably is the reason we're not getting some buy-in. Right? I don't see the dollar value as to how does this save DoD money. Right. I think when it comes down to it, it's going to be how do we market it to say, hey, here is how much it's going to save us. If you invest this amount, here is how much, and this is your return on investment, and this is your rate of return.
Yes, thank you. Excellent question. And that's when our project started. When we started this project in 2019, the naval facility that we work with, they had solar panels, but they could not justify the cost of batteries to increase energy resilience. You can't, I agree. They're too expensive and you're not going to get a return on investment. Right now, with the cost of batteries, the only way that you can justify them is if you say that you're going to be more resilient. That's the only right now. The cost of batteries is going down as we speak, as more consumer electronics and electric vehicles are using batteries. And of course, there is new research on new types of batteries. And here at NPS, there is an effort to do battery research within the energy academic group. But right now, they're still not cost effective. So yes, when they install the solar panel with an EPS, energy performance, EPC, energy performance contract, they could not do the same thing for the battery because it's just not cost effective. Yeah, so you touch on a very key point. From the cost point of view, we yet have to justify it. But things are changing, and we are developing also life cycle cost tools that may give us different answer depending again on the mission and on the life cycle of the base. Yeah.
So, Professor, I wanted to follow up on your answer to the lieutenant's question, because we've been treating energy storage is just kind of a black box. And as a layperson, I think of two types of energy storage, which might be completely inappropriate. So one is local, you're talking about EVs or a battery pack in your house or something like that. And the other would be going back to your earlier pictures of kind of centralized, right? Like the coal power station, you have the equivalent of the coal power station for battery energy storage. So up at Moss Landing, we have a huge battery backup. It's my understanding that China is building a one-a-day fake lake where you pump the water up during the day with the photovoltaic cells, and then you have it run turbines overnight. We're doing 2 a year. They're doing 365 a year. So as my understanding, I might have the numbers off, but I don't have the order of magnitude off. It's multiple orders of magnitude between what PRC is doing, what we're doing. So how does big energy storage versus kind of more local energy storage affect the story of microgrids that you're talking about?
Yes, so there are two different things. Conceptually, they work the same way. The technology works the same way. You store energy, or you get energy. But as the utility is deploying more and more renewable energy, they need also the energy storage, and that's to be on large scale. Because once you have these gigawatt solar farms, you need to have energy storage to compensate. It's back to the point I was making about these large generators. The renewable energy do not have the inertia of the large generators that are in the classical plants. So you need to add energy storage with the renewable energy. So if you have these gigawatts PV farms or wind farms, you need to add storage. And at the big, on the big level, you can, I mean, up until now, because there hasn't been so much PV deployed, you could get along with, go forward with just small energy storage localized. And there are games that can be played if you work with the community, if the consumers are willing to give you control of their houses and their energy storage, but it's difficult. So at the utility level, they're going to large scale energy storage. This is for the Department of Defense is a different story. The Department of Defense does not want to rely on the utility power. So not even on the large scale storage. So that's why we're going with the concept of nanogrids that we are advocating here at NPS, because if you are going to be independent and you're going to be resilient when you lose the outside grid, you need to have local storage too. So it's not going to help the DoD that there is all these huge energy storage plants deployed by the utilities. Yeah.
Hi, Giovanna. So the discussion, I really liked where you talked about that it's resilience, that's the value proposition, right? It's resilience. And wanted to know what you thought of what a resilience performance specification might look like. The only thing I've ever seen is the graph you've shown, and good resilience is smaller time between time down and time back up. But that seems kind of simplistic to me. I was wondering if you had thoughts about what a resilience performance specification. So if I wanted to buy resilience through a microgrid, not the microgrid itself, but I wanted to buy resilience, how would I express that?
Okay, so this is now outside my area of expertise. Resilience is really the field of system engineers. So either Professor Van Bossit or Professor Giachetti can answer this question in more details. This picture is as far as I go, as far as the resilience. That's why microgrids are multidisciplinary team. Not one discipline can answer all the questions.
It's gonna be me. I think that's a good question to start with. So the services are defined in a very simplistic terms. For military base, they want 14 days that it could go alone without being connected to the grid. So that's at kind of a facility-wide level in very simple terms. Otherwise, I think you would have a set of specifications on different aspects of resilience. It's a multi-dimensional concept. It's not a single measure. So you can measure the vulnerability, the recovery time, and there's different aspects that you could put specifications on if you wanted to. But thank you.
Thank you.
Another online question here. What sort of standards are in place to ensure that different equipment from different vendors can easily interoperate in a microgrid setting?
Yeah, this is an excellent question. And recently, let's see, I have one. There is this document, the Unified Facility Criteria, that it's going to come out soon. We actually, our tools were cited on it. It's 355004, Resilient Installation Microgrid Design. This is one documents put together by the tri-services. Over 100 people, including people from our team, have been participating in putting together this document. So this document and other that will follow should be able to answer this question. It is an excellent question and is a big vulnerability of these microgrids when different vendors put together different pieces. And sometimes a vendor goes out of business and you don't have anybody to maintain the one piece. So it is an excellent question, and hopefully we're starting to answer by creating documents like this one. I guess one last question because it's 4 o'clock. Yeah, over there.
Thank you, Giovanna, for a wonderful talk. I would like to just connect to some of these questions that just was going through my mind. What Lieutenant was asking about the cost. And when we talk about resiliency, since there is a 14-day number, and you were talking about earlier about the cost of food per refrigerator, I think probably every facility should know roughly if there was no power for a day, this much money would be wasted. And in our case, maybe if we all went home and got paid, that's the cost. So that I'm thinking that that we should be able to calculate in some ways what is the cost, so that we can kind of have in addition to resiliency, at some point have a number of the savings or money.
Yes, I agree, and we are working on it. Cost analysis has been part of our goal for the last couple of years, and it will be part of the tool here. In fact, one of the reasons why they included us in the UFC was because we are providing several aspects, several tools to design microgrid. But yes, so we should be able to pinpoint some cost. It's not easy, but we're working on it. Yeah.
Great. Done. Hold on. I gotta play.
I'm not a business major, so maybe someone else should comment on this, but if you think about the cost of the resiliency, you need to put in there the cost of sending all your employees home when the power goes out.
Yes. Yeah, that's one part that could be probably easily calculated.
Sorry to cut in on the cost conversation here. Another aspect of this is if you're in nominal conditions or not. So when I think it was Camp Lejeune got stomped by that hurricane a few years back, power went out for several weeks. That place is a training facility, right? It shouldn't be critical. What happened was most of their buildings got black mold because the AC was out. They had to tear them all down, stop training for 3 or 6 months. That's a small incident. Now you're talking about mission assurance and whatnot. Suddenly you have to relocate everything that base does somewhere else if the power is out for an extended period. So the costing part gets really tricky. And that's why there's a big difference for DoD versus civilian.
Thank you. Yeah.
And I think the real importance here is thinking both in terms of cost and tying resilience to the warfighter advantage. Because you're saying, here's how our combat capacity is damaged. What's the dollar number for combat capacity? I don't know, but that's what the whole mission of the Navy is about, is projecting force. And so our ability to project force is either augmented or hurt. And that's the key. The cost, I mean, the dollars are all, we know that's what makes things run. But in terms of being mission critical, right, it's all about the warfighter advantage. And that's got to be part of the story. And I think when you're going with resilience as the key, as opposed to cost, that's an easy link then to make into warfighter advantage. And we could go then to that. You can say, okay, here are requirements for the type of resilience that we need in order for these capacities to be as effective in projecting force as they need to be. I think that's the sweet spot for that.
Yes.
All right. We're going to gather for refreshments outside. You need to eat them all because otherwise Julie and I have to carry them back, which probably means poor Julie. And so please eat all of them. If you care for Julie, eat the refreshments. She'll appreciate that. But let's give a big shout out of thanks to Giovanna. So great questions, great discussion. Thank very much all of you being here. Thank our online audience. Thank the team that made this all possible. Giovanna, outstanding. Thank you so much.
Thank you so much for inviting me.
That's great. You nailed it. Very